Okay, here we are again. This is another lesson on topic of polar coordinates. Actually, you should read the textbook. I can only cover some highlights, but we're going to be working on converting equations from rectangular to polar form. And this is generally fairly difficult, and the results are not always easy. So I'm, of course, selecting problems that'll work out nicely. But as I said, in general, this is fairly difficult. All right, so we'll do 3 examples. And then in the next video, we'll go the other direction from polar to rectangular. So here we go. First example is what we recognize as a line in rectangular coordinates, and we're going to try and write it in polar form. And, we just use the basic ideas that x is r cosine theta, y is r sine theta, and it works out very easily. Watch how it works. All right, so x is r cosine theta, y is r sine theta, and that doesn't look too nice. I guess you could stop there, but generally what we'd like to do is we like to put it in the form of r equals f of theta. When we do rectangular coordinates, we generally want it in the form of y equals f of x. So easy way to do it here is just factor out the r. And then divide. And there we go. So this would be the polar equivalent. There are some domain issues, as you'll figure out when you do the self-directed graphing exercises, but basically this is the result. Okay, so not that obvious, but nonetheless, it does work out correctly. Okay, let's do a second example. And this time we will work with a different equation. We'll work with a line, x equals 4. And again, we're going to write it in polar form. Okay, so here we go. Let's start again. And there are numerous examples on the polar example worksheet that I gave you. Solutions are worked out on Blackboard, so you should definitely try those. So here we go. Okay, x equals 4, which we're supposed to know, and x in the xy plane would be a vertical line going through 4, 0 in rectangular coordinates. So what we're going to try to do is write this in polar form. Okay, so x equals 4. And again, we use x as r cosine theta. And again, solve for r, because in polar form, r is a function of theta. Okay, so we get 4 over cosine theta. And that's pretty easy. And I guess if you wanted to, you could write this as 4 secant theta, but this is sufficient for our needs. Okay, so that was pretty easy. Let's now do a tough one. So, whoops, I forgot to change that to example 2, but right now we're going to example 3, so that's what we'll do. Okay, so here we go. This is example 3, and this one is going to be a little bit more challenging. And this time, we're going to take x plus 3, a quantity squared, plus y minus 2, a quantity squared, equals 13. And you should recognize this as the standard form of a circle. All right, so when all is said and done, what we should get is we should get a circle centered at -3, 2, This would be radius squared, so the radius would be a radical 13. Okay, so again, a circle centered at -3, 2, with a radius of square root of 13. Okay, so the method is the same. The algebra is just a little more demanding. So x is r cosine theta plus 3, and it gets squared. Okay, and the y, of course, is r sine theta. That gets squared. And hopefully you can see I'm going back again to this idea of x is r cosine theta, y is r sine theta. And then we're just going to do the algebra. This is squaring a binomial, so you get the first term squared plus twice the product of the first and second term plus the second term squared. So you get r squared cosine squared theta plus twice this, 6r cosine theta plus 9. And over here, we do the same thing. We get this squared, in this case, minus twice the product plus this squared. So you get r squared sine squared theta minus 4r twice the product sine theta plus 4 equals 13. Notice how I cleverly planned this out to meet the edge of the board. Would have been nice if it was horizontal, but that's life. Okay, now here's where it pays to understand patterns. If you take a look at this term and this term, you're going to notice that they have a common factor of r squared. So what I can do is I can factor out the r squared, and I get cosine squared theta plus, over here, sine squared theta. And I guess if you want to, you can also notice that you have a common factor of r, those two terms. So I guess at the same time, I can factor out the r from those. And I get 6 cosine theta minus 4 sine theta. And again, it's little things that we have to notice. I'll do this in green. You can see you have the 9 and 4, which is a 13, which completely balances out the 13 there. So our experience from solving equations, you could subtract 13 from both sides. You're going to get a 0, which, as you're going to see a little later, very helpful. Okay, so now the idea is you're looking at this, and you should know this. This is the most famous of the Pythagorean identities. That's a 1. So you get r squared plus r times this quantity, 6 cosine theta minus 4 sine theta equals 0. And, perhaps because this is a 1 right here, okay? So r squared times 1 is just r squared, and I just brought this term down. Okay, so the idea now is, basically, this is like a quadratic equation. It has the same type of pattern. You have variable squared, and you've got equal to 0. So I can factor it, and I get, if I take out the r, in fact, let me make this a square bracket here. Okay, you get plus, what do you get? You get 6 cosine theta minus 4 sine theta equals 0. So you get either r equals 0, which is a point. It's what we call the origin, but in polar coordinates it's called the pole. And over here, well, let's see what happens here. This is a typical linear type of equation. So what I'm going to do, and I would set this equal to 0, and I'm running out of space. I'll just say it. I'll set this equal to 0, right? Because I've got a product of two quantities equals 0. one of them has to be 0. So either this is 0 or I've got this is 0. So I'm going to have r plus this quantity equals 0. And if I want to solve for r, let's see the way this works. Okay, and now what I would do is I'll get these over to the other side, and I get r equals, notice this goes over, it becomes positive, because when you move a term, you change its sign. This becomes negative 4 sine theta minus 6 cosine theta, and there we go. That would be the equation of the polus of a circle, which is, what do we say? We said centered at negative 3, 2. So I'm going to make a rough sketch here. Negative 3, 2, centered about there, with a radius of radical 13. And it turns out it's going to go through the pole or the origin, we're saying, and that gives us our r equals 0. So if we, my drawing is probably something like that. Not a very good job, but you know. Okay, so that would be this circle in polar coordinates. Okay, so you should definitely practice the problems that are on that worksheet that I handed out in class. There's an extra copy on Blackboard, and the solutions are pretty much worked out on Blackboard. And this is probably the most difficult that you would be expected to be able to do. But, you know, again, notice we're using the basic ideas we've seen before. We got a Pythagorean identity, comes out to a quadratic, we factor. So this is all the kind of stuff that we've seen in the past. Okay, so the next video will be the same type of thing, but this time we'll be going from polar to rectangular, and we're going to come across some of the same issues, and see you then.